All right, hey everybody. Welcome to Calculus One. I'm just going to jump right into the topics. Our fundamental idea of study is the idea of a function. So that's what we're going to start talking about today. Um, Most of the mathematics that we've probably studied before now, the things we're mostly studying are numbers, right? We learn about numbers, we learn to count them, we learn to do operations on them, right? The ways in which they interact, and even algebra. We're learning how to manipulate things that represent numbers. Numbers are still the kind of main focus. Um, there's a few other topics in there, geometry being one of them, and depending on what direction you went in. But numbers have been the main thing we've studied in mathematics. Uh, as we go through this pre-calculus course, right, preparing ourselves for calculus, uh, what we'll find in calculus is that the thing we're studying probably more than numbers is functions. We start to think of functions as the things we're interested in, right? There's numbers still in there, as we'll see as we go forward, but these functions are like the things we start playing with, the way we've manipulated numbers. And so we'll see different actions we can take on them, combining them, how they interact with each other, and other things, and so forth. So the fundamental thing right now is to make sure we understand what a function is. So let's start there. Let me give you a definition of a function. There are different ways we can define them that should all be equivalent. So this is the one that I like. We should think of a function as, we can say, a function is a rule that assigns to each element in a set. I'll call it A. In a set A, exactly one element from a set B. All right. So we often will call, let's just say, we'll call A the domain, and we'll call B the range. All right, more on those later, but that's just how you'll hear them referred to. Okay. Um, all right, so let's talk about what this means. We're also, besides studying functions, moving forward with your mathematical, let's say, sophistication. And so, one thing to note is in definitions, being very careful about exactly what is being said. For example, there's nothing in the way this is written that implies that A and B are not the same set. They often will be the same set of things. Um, or they could be two different sets, right? Both of those are acceptable. So it doesn't really specify whether or not they're the same. They could even not be the same kind of things. We'll talk more about that. We should just say what a set is. We can just think of a set as a collection of things, right? It might be the set of all the even numbers, or the set of letters in the alphabet, or the set of names of students in a class, right? Those are all sets. And so we'll most typically in this course be dealing almost exclusively, other than a few examples here and there, dealing with situations where A and B are both sets of numbers, maybe all of the numbers, maybe some smaller collection of numbers from all the real numbers we have. Um, so we've got this idea that this function, this rule, if you give it anything from the set A, from the domain, it assigns to it a different element, or sorry, it could be the same element, assigns to it, but the key feature is that it assigns to exactly one element from the set B, right? The range. Right? Sometimes we draw this in a picture, right? If this circle represents the set A, you can imagine there's just a bunch of things in that circle. And our function, if I pick one of the things in that circle, I'll use the lowercase a for that thing that I'm choosing, then our function tells us, oh, there's something over here that we're going to assign to that element. And there's only one thing over there. All right. So let's just do an example of a function. And we're going to kind of see as we're going that there's lots of ways to represent functions. For example, I could write down a set of ordered pairs. I'm going to take a function where the domain, I'm going to give this function a name. Let's just call it the alphabet function. Or let's just call it the alph function. And this is going to be a function where I'm going to take a letter from the alphabet. So the alphabet is going to be my domain. And I'm going to assign to it a number, let's just say its place in the traditional order, right? The A, B, C, D, E, F, G, right? That order that I'm most familiar with. Right, that's our range, is the numbers that will define the order of the alphabet, right? So we have our domain is all these letters, and its place in line, let's say, is the range. If I want to represent this function, well, another way I could do this is I could write down, we often think of them as ordered pairs. So I can write the letter A would be assigned the number 1. The letter B would be 2. The letter C would be 3. I'm not going to write all of them, but we'd get down to Y is the 25th letter, and Z would be the 26th letter. Right? So in this way, I've completely represented the function, or if you imagine that I wrote them all out, we've completely represented the function. All of the first coordinates in these ordered pairs are the letters, and the second coordinate is the place of that letter in the alphabet, right? We will typically think of our functions when we we'll always think of them this way, but written in ordered pairs, we think of the domain values as our inputs and the ranges as our outputs, right? So it's almost like we're asking this function a question. Hey, what place in the alphabet is C? So my input is C. I'm giving it the letter C and asking it what place in the alphabet is this, and it gives me back the number 3. Okay. This is one of the reasons we have this line over here, this phrase over here in our definition, that we assign exactly one element from set B, because I don't want to ask the question, what place in the alphabet is the letter D, and my function says it's 4 or 7. I want to know the answer, right? I don't want some options to choose from. The function is supposed to be telling me the result. And so that's a big reason for that, right? Functions we'll see later on, right? We use them in science, math and science, we'll construct what we call models, where a function can represent something happening in the world. And often we can think of it as a question we want an answer to. What's going to be the high temperature on Wednesday? And the meteorologist has some function that's way more complicated than I understand, but they can spit out a number and say, I predict it to be 73 degrees to be the high on Wednesday. We wouldn't be very happy if their model said, well, it might be 73 or 95, or maybe it's only going to be 45, right? We want an answer, right? Whether or not their prediction is right, we want to know what their prediction is. Let's see. Oh, let's do another example, which will also give us another way to represent this function. I'll pull this from my syllabus. Let me grab. Right here, I have a table. This is the grading scheme in my course, where I'm converting from a percentage to a grade on the 4-point scale, right? And so this we can think of as a function that goes from the, let's just say, the percent earned. Let's call this function, we'll call it FG for final grade. my final grade. You get your percent earned, and so right, that's going to be a score between 0 and 100, and the output is going to be its corresponding value on the 4.0 scale, right? So it's going to be something between 0.0 and 4.0, right? And so I haven't listed all of the values. Right here are our inputs are going to be your percentage, and right, that's any value between 0 and 100, not just whole numbers. You can earn a 95.653 in this class, right? And so I'm just listing some of them here, but the table still gives us an idea of how this function works, right? You input a 95, somebody gets a 95% in this course, they get a 4.0, right? And you can, if you read this carefully, this also means if they get a 96, 97, 98, anything above 95, right? For all the numbers between 94 and 95, so 94.0 through up to 95, you'd get a 3.9, right? And so on and so forth. So you can, this helps define that function, right? Same idea. We have an input, and again, let's reinforce this idea that we're getting exactly one output. You would be very frustrated in this course if you had an 88% average, but you didn't know what that corresponded to. That my final grade function told you, well, you might get a 3.3, or maybe it'll be a 2.5, something like that, right? That would be a very dissatisfying answer to that question. Our function should have one output, okay? All right. So, more typically, let's go to a new page for this. More typically, the functions we're going to be most concerned with for this course are going to be more mathematical functions, where our input is going to be a number. The function, the rule that assigns it an output, is going to be some mathematical construction. For instance, I could have a function f. Let me just give it a name. And my function might be, given a number, let's say given a real number, multiply by 3, and then add 7, right? That is a function, right? I'm implying in this statement, given a real number, that I'm starting with a real number, and presumably any real number, because what I'm asked to do to it is to multiply it by 3. I can take any number and multiply it by 3, and I can add 7 to that result, right? So for example, if I started with the number, for instance, 2, my function would tell me to take 2 and multiply it by 3 to get 6, and then take 6 and add 7 to get 13. And so let's go back to one of these diagrams. If I think of this blob as being the set of all numbers, call this my range. I looked at the number 2, and my function f said, oh, I'm going to assign to f the number 13. Right? Our input is 2. We follow the instructions given by the function, and we end up with the new number 13. So there's where the rule assigns our new value, right? And if we take another number, let's say 1, we input 1, we take 1 times 3 is equal to 3. We take that and add 7 to it, we get 10. And so I could say the number 1 goes to 10. Okay? Right. Now, let's do 2 more functions well, let's do 1 more function in this way. Let's take the function g, for instance. And I will say given, just giving it the name. By the way, these names are arbitrary, though we'll see as we move forward. F and g are going to be common numbers. We can name our functions whatever we want, such as what I did above. FG was one function, the ELF function, right? It's a rule, and I just want to give it a name. So we can name them whatever we want. We'll often use F or G. Just like in algebra, when you had an unknown quantity, we often called it X, but there's nothing telling you have to call it X. You could call it K, or you could call it Z, or you could call it Y, or whatever you want to call the unknown and manipulate in the same ways, but we'll often use F and G for our functions. So in this function, given a non-negative real number, find its square root and divide by 3. All right, the writing's looking a little sloppy at times. I might need to get a new pen for this. Okay, so it's a similar kind of thing. Notice now that our domain is not all the real numbers. It's only the non-negative real numbers. So that's all the positive numbers and 0, right? And the reason for that is that first step, finding the square root. We're only going to be dealing with real numbers currently, and so we don't have square roots of negative numbers. Down the road, we'll find a kind of number that lets us deal with that. But for now, that's a forbidden operation. So let's just do some examples here, and I'll make some nice, easy examples for me. Let's say I start with the number 9. My first instruction is to take the square root of 9. And maybe I should be a little more specific. We'll say it's positive square root. When we say the square root, that is what we typically mean, and we've all decided, by we I mean humanity, that when we say the square root, we mean the positive one, but I'm gonna get explicit right there. Right, because 9 has two square roots, -3 and +3. But we'll take the positive one, so we take the positive square root is 3. Then our next step is to divide by 3, and we get 1. So my function G, if we start with the number 9, and we do this kind of diagram, takes us to the value 1. Right, that's what it assigns. And just for good measure, let's do one more. Again, I'll make it easy. 25, we take the square root, and we get 5, and then we divide that by 3 to get 5/3. So 25 is taken over here by G to the number 5/3. Right? So, and don't let the fact that I'm choosing nice, easy numbers, this also works for not perfect squares. I could do this for 8. We'd have the square root of 8, which can be written as 2√2. Either way is fine. And then we divide it by 3 to get 2√2 over 3. And so I'm not going to draw that in there. It's getting messy, but you can imagine that we can draw another out, right? These little blob diagrams are really only good for getting your head around this. They're not a very convenient way to represent functions because they obviously fill up pretty quickly. So you might notice already that this is a kind of cumbersome way to talk about functions, to have to write out in a sentence what they are. So we have another way to represent functions that we'll talk about now, which is called function notation. Function notation takes that rule, like multiply by 3 and add 7, and gives us another way to write it. So I had called that function f. And what we do is next to the name of the function, we put a set of parentheses. Okay. Now, well, I'll finish this and make a comment. What we write in here inside the parentheses is a symbol. I'm going to use the symbol X, but any symbol will do. And we're saying that X represents the input to that function, the element from the domain that we're going to do something to. In this case, remember what we did. We took that number, we multiplied it by 3, and then when we were done, we added 7, right? So that little set of symbols represents this statement. Given a real number, multiply by 3, then add 7, right? Here, x is representing that real number, and we can see that we're multiplying it by 3 and adding 7. Now, whenever we have a function, there's a domain. What we'll end up seeing is that the domain is often all the real numbers. And so we just neglect writing it often. But I'm going to make a habit of, at least in this beginning, writing it. In this case, the domain is all real numbers. Okay. A few ways. Let's write this in a couple ways to see some of the things we have. Some of the ways you might see it written. Sometimes we might write x. That's representing the input. We can use this little Greek letter that we can just see say as like x is in the set, and then this is a symbol for all the real numbers. That's much more common later on mathematically. You won't see it much right now. We sometimes write it like this. We could say x, since it's any number, x is going to be between negative infinity and positive infinity. We could also write an interval notation, right? That means, again, between any number between negative infinity and positive infinity, which is all of the numbers, right? So you do not have to write all this, right? We will find as we move forward that we often don't write anything. There's going to be an implied domain. We'll talk more about that down the road. And if you write anything at all, you really only need to write one of these. I just wanted to show you some examples of that. Okay. But the important thing right now is notice we have this, sorry, I just want to give us a little more space. This nice, succinct set of symbols that completely represents that rule, right? And notice how much more compact it is than writing out that sentence, given a real number, multiply it by 3 and add 7. Then I had this very clumsy way of writing out how we say went from the element 2 to the element 13 using our rule. This gives us a much more elegant way to do that, right? So the way we say this is f of x is equal to 3x plus 7. If I wanted to evaluate this function, that's what the language we use when we take an input and find out what its value is, what the value of the function is when we put that input into it. We evaluate the function. So we would say f of 2 is going to be 3 times 2 plus 7. Right, and then we could write 3 times 2 is 6 plus 7 is 13. So we end up with f of 2. Sorry, that f looked kind of janky. We end up with f of 2 is equal to 13. Okay. This line right here at the end, a couple of things about this. This completely represents the same thing we did before, where I drew those little clunky diagrams where I went from 2 to 13 by way of f, because in this set of symbols, we know that 2 is our input. And we know that if you take 2 and input it to the function f, right, our function is right there, that it gives us the output 13, right? All of that information is stored in that little compact set of symbols. Okay. So this is always how we think of our functions, right? This is our input. This is the name of the function. And the rule is written on the other side. And this rule will give us the output, right? It leads to the output. Notice this also means, let me write this down here again, f of x, this whole thing together is the output. right? Look at what I have in the red box. On one side of I'm going to rewrite it. Oh, I don't know why it just stops working sometimes. Let's try again. Let's rewrite this. F of 2 equal to 13, right? I've got an equal sign. What that means is, I mean, this sounds obvious, but the things on either side of the equal sign are equivalent. And I just got done telling you in this red box that 13 is the output. F of 2 is equal to 13. So this whole thing must be the output because it's equal to the output, right? So this is a really wonderful symbol, right? It's got the name of the function. That looked terrible, but I'm not going to erase it. And we've got the input. And then collectively, that whole thing represents the output, the thing that gets reported when we do the input, whatever it turns out to be. In the example case, we did f of 2 is equal to 13. Okay. And sometimes we will give this whole thing the output its own name, typically y, right? And so that's just another symbol that we use often. There's a lot of notation right now, right? And I understand that. So you're just gonna have to practice it. We'll keep reminding ourselves of what all these things mean. And hopefully you've seen this a little bit, but even if you haven't, we're gonna see it a lot in the coming days. And so some of this it'll start to sink in. Let's look at that other function that I had written up above, g, which remember was given a positive or non-negative real number. So we take its square root and divide by 3, right? There's that whole rule. And the domain is x is greater than or equal to 0, right? And again, we can write evaluations very easily. G of, let's say, 1 is just the square root of 1 divided by 3. The square root of 1 is 1/3. Sorry, is 1. So we end up with 1/3, right? So I didn't mention this above, and I meant to. Let's mention it now, right? The way we evaluate is given our rule. So here the rule is written abstractly up here. When we replace the x here, right? This was written as x up above. We replace the x here, right? So it's a really, really simple idea. There's this parentheses that when we don't know what the input is, we use the symbol x to represent the input. When we put something else there, you just say, oh, well, where was x in the equation as written? Let's put something else there. Let's put that thing there, right? You can think another way we can just think of this. This is going to be less. This is less convenient, which is why we don't write it this way. But we're just saying, given the input, take the input, take its square root, and divide by 3, right? That's kind of the long form way to write that. Okay. What else was I about to say? Let's give ourselves one more function. We haven't seen this one before, but I'm just going to write this one out and do some examples with this. H of x is 1 over x plus 3, right? If we had to write this out in a sentence, we would say something like, given a real number, and we'll have to qualify that in just a second, but given a real number, take its reciprocal and add 3 to it, right? So if I'm given the real number 5, I could take its reciprocal, 1/5, and add 3 to it. Which we could, if we want to do a little bit of work, 3 is 15/5. So we end up with 16/5. So h of 5 is equal to 16/5, right? Notice, let's try to evaluate one more. What about 0? 0 is a real number. and I get 1 over 0 plus 3. And hopefully we remember that 1 over 0, in fact, anything over 0 is not defined, right? Division by 0 is not defined for us. Right? It's almost never defined. There's some weird cases where people decide it's useful to have it defined, but we're not going to ever deal with those cases in this class. So division by 0 is just not defined. So that implies this is one of those things where mathematicians can sometimes be lazy. We should write down the domain like I did over here of every function. We often don't. And when we don't, what we're really saying is this function is defined for every real number that doesn't break the rules of math. So in this case, taking the reciprocal, we can take the reciprocal of every single number except for 0. And once we take the reciprocal of every single number, we can always add 3 to it. So this function will work for every single number except for the number 0. And so when we don't write the function, we assume the domain is all of the possible inputs that don't break math, right? In this case, 0 breaks it. If we were going to write it, a convenient way to write this is x is not equal to 0, which means we're saying everything else but this, which is it's just easier than writing down all the numbers. It's not, right? Otherwise, we'd have to write something like this, like x is less than 0 or x is greater than 0. Or something like that, something more convoluted. So we just, when there's just one or two numbers that we have to outlaw, we'll just write those down, and then the assumption is all the rest are allowed. Okay, so there is our, there is another example. And there we see a domain that we have to, this idea that the domain is implied even when we don't write it. I'll continue writing them a lot, but we'll see as we go forward. We'll eventually not always write them down. But we just got to get used to remembering that they still exist. We'll also find out, and we'll see this much later when we're using these functions to model the real world, meaning x might represent something in the real world and the output represents something else. And there might be some constraints that aren't mathematical that make sense for the domain. But we'll get into all of that later. Right now, we'll just worry about mathematical domains. All right, one other thing before we get into our last big topic. Let's go back to that original function, f of x equals 3x plus 7, right? So we've already seen doing a couple inputs. Let's just do one more. Let's say f of, let's do f of 2/3 is equal to 3 times 2/3 plus 7. 3 times 2/3 is 2. Man, this is getting hard to write with. It's like there's a lag. It can't keep up with me if I write too fast, which I guess is good. I should be writing slow. So there we go. F of 2/3 is equal to 9. Right? Input is 2/3, output is 9. Sometimes, and this is the kind of thing I can't give you a great example of right now. But there will be good reasons where the inputs we want are going to be symbolic of something else. For example, I may want to compute something like this. What if I wanted to know what f of, well, here, this will be a good example, f of x plus 1 is. All right? What I'm saying here is I'm just letting x plus 1 represent the input. Right? So let me rewrite my function down here using this more cumbersome notation. It's getting really slow. It really can't keep up with me. 3 times the input plus 7. Right? So with that in mind, right, what this is telling me to do the instruction is not different, right? The instructions right here are take an input, multiply it by 3, add 7 to it. Our input right now is x plus 1. I want to multiply that by 3 and add 7 to it. That's it. We just replace whatever's put in the parentheses, we put in the place that x went in the original function, right? Whatever's put in these parentheses, you put it right here. And the fact that we wrote x plus 1 doesn't change that. We take that x plus 1 and we put it right there. Now, we'll evaluate this. We'll multiply. I mean, it is evaluated in a sense, but we'll play with that in just a second. We'll come back to it. But I want to just show you a couple common errors before we get there. So I'm going to do this over here. So I think these will illustrate some things. F of x plus 1. One thing I often see is just 3x plus 1 plus 7. Right? The big mistake here, well, what happens if we simplify this a little? Well, we've just got 3x plus 1 plus 7 is the same as plus 8. The problem is the function said take what you put in and multiply it by 3. We didn't multiply what we put in by 3. What was put in was x plus 1. We didn't multiply all of x plus 1 by 3. We only multiplied x by 3. So we didn't actually follow the instructions. All right? There was a clear set of instructions, but we didn't actually follow them. So now let's come to our other, let's come over here and do it the correct way. But multiplying the entire thing, 3 times x gives me 3x plus 3 plus 7, or 3x plus 10, right? Notice, obviously, those are not the same result. And so it's important to understand that when we put an input in, it's really as simple as look at the original instructions. You can think of it this way. Wherever that x appears means put the input here. And we have to, when something's done to that input, you have to do it to the whole thing. So when our inputs are more complicated, right, not just a number, but x plus 1 in this case, you have to put parentheses around that thing and do the thing that you're doing to the input to that whole thing, right? We'll see some reasons for this down the road. Here's a fun little result in here, though. Let's just rearrange what we have right here. Let's come down a line, actually. I'm just going to, not to complicate things. So I'm just going to use that second line for a second, but I'm going to rewrite it as 3x plus 7 plus 3. Notice what, right? So all I did was copy this line, but I switched the order of 7 and 3 because addition, the order doesn't matter, it commutes. Notice what 3x plus 7 is, though. That's just f of x, right? That's our original function given the input x. So by increasing our input by 1, right? So we took f of x plus 1. So if we think of f starting with f of x and then we go to f of x plus 1, it's equivalent to increasing our output by 3, right? Well, that's just a demonstration of what this is a linear function, right? You've studied lines before, 3x plus 7, mx plus b. 3 is our slope. The slope represents how that line changes as the input changes. The output changes as the input changes. If you increase your input by 1, you increase the output by 3. And that's exactly what this line is saying. So that's just a fun little demonstration that function notation makes kind of easier. If you haven't thought about lines in a while and that was not super familiar at the moment, give it some thought outside of the context of this video. The main focus here is right now is just getting to comfortable using function notation. Okay. All right. One more big way that we represent functions is going to be graphically, right? I'm going to save that for the next video, but I'll give a hint at it by noting that we already said f, we sometimes give the output the name y. So we've got our input, our output, and then this set of symbols also represents the output, right? Well, way back at the beginning, we had this notion of listing our functions as coordinate pairs, the input on the left, the output on the right. Right? So if we use this new notation and that same concept, then we can think of every input-output pair as a coordinate point. Oops, let's go back to black. Right? So if you have an input of x, you'll have an output of f of x. This is driving me crazy. F of x. Right? So it's a little complicated to look at with all the parentheses, but notice we've got an input x and an output f of x, two numbers. It's just a coordinate pair. Like, for example, we saw up here the input 2/3 gave us the output 9. Right? That's a coordinate pair. We can take this idea, which we'll do in the next video, of starting with a function. We get these input and outputs, and we get coordinate pairs from those, and those coordinate pairs can be put into a Cartesian coordinate system that you've seen before, and get the graph of a function out of that. So that's where we'll head next.